Okay, thank you, Cloud Voice. Let me hide the meeting controls. Oh, you know what? Let me put this on Do Not Disturb. It syncs with my laptop, and you don't need to hear my spam calls. Apparently, the IRS police are after me. Go figure, unless I call and give them my social security number and all sorts of other stuff. Okay, Do Not Disturb. All right. So, good morning and happy Friday. Today, our purpose is to talk about counting. Well, what do you mean by counting? We'll get to that. There are scenarios where the events and therefore the sample space over which we define our probabilities are really hard to enumerate. Let me close that. Okay, so hopefully, let me just do this. Check. Mic is still hot. And let me make sure. Yep, that's still good. Let me hide meeting controls. Okay, so we're going to be talking about counting. But before we begin, excuse me, some administrative bits. The reading has not changed from last time. I've curated a pretty nice and accessible stats book as a Google Doc available that I've curated and made available on the course resources section. And so this is if you like the book modality, it's there for you. Stats hasn't changed for a really, really long time, several generations. And I was going to say something funny about the dog GIF, but I can't remember. Like, what do you mean another book? Anyways, I can't remember. All right. So we'll start off with a little bit of something to get your, analytical juices started. So one day, walk into a coffee shop, and there are two folks in the coffee shop, two gentlemen, and one of them, person A, and the other person B, you don't know. And so they're chatting, and after that, you get your coffee and you say hello, and then go about your way. You see your friend again on Monday morning, and you ask your friend, who was that person B? And your friend answers, brothers and sisters, I have none, but this man's father is my father's son. So, what's their relationship? What do you think? I wish I had Jeopardy music. What do you think? What is their relationship? Brothers and sisters, I have none, but this man's father is my father's son. No? Brothers and sisters, I have none, but this man's father is my father's son. Want to know the answer? It's a father and son. Person A is the son, and person B is the father. Brothers and sisters, I have none, only child. This man's father is my father's son. This man's father is the grandparent of A, and the son of the grandparent is B. Okay, all right. So why do you do this at 9 o'clock in the morning, right? Okay. So we'll also have to figure out how to do it. Try to have a group exercise on Monday to kind of mix it up a little bit, as well as some of the feedback from last time I taught the course. Okay, we'll have to figure that out. I'm trying to gamify it, but it's kind of a lot more challenging to fit that in the space of an hour and 15 minutes. All right, so why don't we get started? Where we last left off, so how's everybody doing? Ready for Friday, ready for the weekend, right? I see, I hear you. So when we last left off, we talked about a little bit more formalism, excuse me, for what a probability is. And for this, we introduced this idea of a so-called sigma algebra, script M, in the diagram that I presented. And so we talked about this script M. And when we did so, we said it represents all sorts of collections that you can assemble from what we were calling our sample space omega. Okay. And for this, we then motivated this idea, excuse me, of a litmus test that defines whether a set qualifies as this thing that we called our sigma algebra. And the reason for this is that these litmus tests, these requirements, if your set passes each of them, then you can associate probabilities or real numbers between 0 and 1 on the closed interval on the real number line. You can associate probabilities with each member of this particular set, our sigma algebra. And so we motivated it, and we looked at all these three litmus tests, and we had the full example of the so-called dense sigma algebra, which is the set of all possible subsets that you could draw from the sigma algebra. And we said this included the anything event, which for the die roll was that set of 1 through 6, which was exactly our sample space omega. It also includes the complement of the anything event, which is the nothing event, our empty set. And then we said, what if you included all of the so-called one-way outcomes, side 1 through side 6? And then our sigma additivity, that third litmus test, built up this idea of complex events. And so we built them up 2 at a time for the so-called 2-way events, the 3-way events, 4-way events, and the 5-way events, or collections of events. And it just so happens 2 of the 3-way events, the event 2, 4, 6, that complex event, we give a name to it, the evens, and its complement, the event, which is the collection 1 through 5, that's the odds. Okay. Any questions about this? Jar your memories? Yeah. All right. So then we talked about this idea that took advantage of sigma additivity. And the idea was that you can build up these so-called complex events by the union of so-called simple events. And knowing that it is the union or the combining of simple events, you can construct the probability of this complex events by literally counting the number of outcomes in your complex event, E, and dividing by the number of outcomes in your sigma algebra, the cardinality of our sample space omega. And so sometimes when you read through the literature, be that textbook or publications, they'll often call the numerator of this expression for our probability the so-called favorable outcomes. And the denominator, excuse me, is our set of possible outcomes. So this idea of counting is really important, and it's very straightforward for finite, relatively small sample spaces, omega, corresponding to things like the outcome of a die roll, but it gets a lot harder to count when these events in which you're trafficking in, therefore our sample space, are much more complex. So complex that in statistics, we adopt a set of heuristics to help us in counting, be that the total number of events possible or the number of so-called favorable outcomes. Okay, any questions? No? So we're gonna go back to school, so to speak. And I remember when my daughter was really little, she loved Sesame Street. So this is about counting. Okay, so complex events. A complex event is, well, I'll use the word complex, but it's one in this context where it's not so easy to enumerate all the possibilities. Now, certainly the prerequisites for this course are Calculus 1 and CS120, the Intro to Programming. But if you've taken a combinatorics course or a discrete math course in computer science, then a lot of this is going to be old hat. So here's a complex event. We need to know, certainly, we said the cardinality of all the possible observable events, our sample space omega. But then when you enumerate or count these things, it's not always so easy. So suppose you were picking, I used to say soccer, someone corrected me, it's football. You were picking a football team, and that football team was comprised of Clark students, undergraduates, during the fall of 2020. And let's imagine then the constraint was it had to consist of 6 female and 5 male students. Now, of course, if you wanted to describe the probability of picking a particular selection, it's not so easy to think about that. And this is an example of what I'm referring to when I say complex events that are much more difficult, for which it's more difficult to enumerate all of the outcomes. And so for such problems, we rely on these heuristics that help us evaluate the structure of the observables. And we use these heuristics to help us to enumerate or count the various outcomes that we can make. Okay. Any questions? Does that make sense? No? And so more general, we talked about the number of favorable and the total number of observable events. I'm going to try to maintain my distance here so I don't get anyone else sick. And let's just note this as n sub t for the total number of events, that denominator for that expression for probability of a complex event, and n sub f as the favorable events. And so in either case, whether it's nt or nf, you need to be able to enumerate all of the possible outcomes. So how are we going to do this? Okay. Well, two of the major considerations is when you try to count, you think of counting as making a selection from among a large number of alternatives, because you have these observables, but the possibilities, whether it's NT or NF, represent all the different ways you can build collections to form your complex event. And so when you make the selection, two of the considerations are, do you replace them after selection when you're forming your complex events, or do you distinguish duplicates? And I'll explain what I mean in a few slides when I refer to the term duplicates. Okay, so let's take a look at considerations for the replacement question. So suppose you're forming a 3-on-3 football team, and for this team, you have a slate of 7 different players. So you're playing some street ball, okay? And for these 7 players, or that represents the slate or the set of individuals from which you will form your complex events. Now, of course, we're not going to use all the individuals. In this particular example, it has to be a 3-on-3 team. So each team, let's say you have team A and team B, and let's say it doesn't matter which team picks first. And so team A is going to get a pick from our slate of 7 players. Team B is going to get a pick from our slate of players. And then it's going to go back to team A, and they're going to alternate with their picks until each team has a roster of 3 total players. Okay, any questions? Does that make sense? And so in this sort of problem, when you form all the different possibilities, the possibilities in this case that we're counting is the total number of 3-on-3 teams that we can form, right? That's a complex event because it has a lot of possibilities, and it's kind of hard at face value to just think of all the different possibilities that we can count. And so we start out with 7 players. 7 choices is going to be what the first team has to pick from. And so for these 7 choices, let's say without loss of generality, meaning it doesn't matter which one picks first, team A is going to have the first pick. So let's say team A makes their selection. And now when team A makes a selection, that particular player is no longer available for subsequent selection for any other team. And so one of the things you'll notice is the slate of players from which you can select has now decreased by 1. That's without replacement. And so without replacement represents how you form possibilities that you can count. And the thing to remember is the number of choices on that draw when you're forming your team. Now, it could have been Rapinoe, that first pick could have been Morgan or any of the other players. What matters is the number of choices that each team has on their draw. Okay. Any questions? Does that make sense? Okay. So now it's Team B's turn, and Team B has 6 choices from which they can pick the first player. So let's say Team B selects Leroux, my wife would say. Yeah, right. And now you'll notice again, there are 5 choices or 5 players left from the slate of players from which you can select. So then Team A picks, and when Team A makes this pick, Team A has 5 choices. So Team A makes a pick. The number of players goes down by 1 because that player is now no longer available to be selected. And so the count for the number of choices now goes down to 4. Excuse me. So when Team B selects 1, now the number of choices goes down to 3. And then Team A makes a pick. That's the final pick. Number of choices goes down to 2. And then Team B picks Ronaldo. Now the teams are complete. And so if you were to ask the question, how many possibilities are there? You multiply the number of choices that each team has on the first draw, the second draw, the third draw, and that multiplies, and that's your result for how many different choices you have. Okay. Any questions? Does that make sense? All right. And so this idea of replacement, in this case, and it's an example of so-called without replacement. And that means that when you form your possibilities, each time you select a candidate for inclusion, the slate of choices from which you make your selection decreases by 1 because that person or that object, more correctly, is no longer available for consideration on the next draw. Okay, any questions? Does that make sense? Yeah. All right. And so another way of picking, so-called with replacement, says that when you make your draw, you note down what your draw is, but the slate of alternatives from which you pick does not decrease. So you're not removing it from consideration. And in this example, suppose you're drawing something and you have a digital color palette and you want to pick 2 palettes, palette A and palette B. And in this example, the argument is that we're picking different colors, but that's not always the case, right? And so here in the beginning, we have 8 crayons in our crayon box. And, I'm still salty about that as an adult. Yeah, as a kid, I had 8 crayons in my crayon box. I'm still paying for it today because I don't know the difference between sunflower, school bus yellow, and butter. It's just all yellow to me, right? But anyways, I digress. So here in the crayon box, we have 8 possible choices for the colors that can be picked to form our palettes. And so without loss of generality, let's imagine that palette A is going to pick first. There are 8 choices. So palette A makes a draw. And let's say palette A picks purple. And on the next draw, the difference here you'll notice is that the number of colors possible, our crayon box, still has 8 colors. So you're making a selection, but in making that selection, the size of the slate of possibilities from which you can form your selection or draw your selection does not change. It's still available for the next draw, all of the objects. Does that make sense? Any questions? No? All right. And so let's say palette B draws, there are 8 total choices. And let's say B picks red. And then it's palette A's turn again. Palette A still has 8 choices. Let's say palette A selects orange. It's palette B's turn. Palette B has 8 choices because the full slate is still available for selection. Palette B then say picks purple. Palette A gets a turn again. And let's imagine it's just 3 different colors you're choosing. Palette A selects yellow for that third and final color in our 3 color palette. And then it's palette B's turn to pick, and palette B picks green. Now in this case, again, we still multiply the number of choices available when the pick was made. So it would be 8 times 8 times 8 for palette A in terms of possibilities, and 8 times 8 times 8 for palette B in terms of the alternatives. And so the key takeaway is that in this case, so-called with replacement, each time you make a pick, the size of the slate of alternatives does not change from one draw to the next. Okay, any questions about this? And so if you are asked the question of how many different color palettes can I choose with replacement, where we have two palettes, palette A and palette B, you'd have 8 times 8 times 8 for palette A. You multiply that by 8 times 8 times 8 for palette B. Okay. Does that make sense? All right. So the other consideration, oh, I just think I jumped ahead. So for replacement for your selection, the key consideration is so-called with replacement or without replacement. The 3-on-3 football team, that was without replacement. And for that, we saw that the slate of players reduced by 1 each time you made a draw. And that would be the case if you had 2 teams, 3 teams, 10 teams, or what have you. Certainly, if you exhaust the slate of players, you can't continue because you have 0 choices at some point, and 0 times anything is always 0, the degenerate case. But nonetheless, without replacement says each time you select or sample an item, it's removed from further consideration, and therefore the number of possibilities decreases by 1 for each draw, regardless of which team it is. With replacement, that's the color palette example, and it says that each time you make a selection, that selection is noted down in terms of what you draw, but it's not withdrawn from consideration for the subsequent draws from that slate of possibilities. Okay, any questions? Does that make sense? And that is the case regardless of if you have 2 color palettes, 3 color palettes, 10 color palettes, or what have you. Let me just do one thing. Yep, the mic is still on because there's a point in the room. If I go past that, it cuts out and then it goes to the laptop microphone. So the other consideration is whether you distinguish duplicates. And those duplicates have to do with if you consider the order in which you draw certain alternatives from your total slate of possibilities. And so one example, and this is just from a book that I was using, a family plans to have 2 children. And what if you decided the probability of having 2 girls? Okay. Well, one approach you might decide is that there are 3 possibilities you can have for 2 children. You could have 2 girls, okay, 2 boys, or you could have a girl and a boy. And so taking these possibilities together, there are 3 of them. And if each possibility is equally likely, you could argue that the probability of having 2 girls is 1 upon 3. Okay. Now, depending on what your consideration is, this might not be correct. And I'll explain what I mean on the next slide. And so suppose you can have at birth male or female. That's a cardinality of 2. And the other approach considers the ordering in which they arrive. And so in one case, you could have a girl for the first child and a girl for the second child. In the other case, you could have a boy for the first child and a boy for the second child. And then there are 2 alternatives for 1 girl, 1 boy. You could have a girl first and a boy second, or a boy first and a girl second. And so in this case, considering this alternative where you're paying attention to the order of selection, you're distinguishing the order in which they arrive and not just the presence of each of those individuals. Does that make sense? Any questions? No? All right. And so if you were to do it this way, you could say the probability of female and female, well, that's just 1/2 times 1/2 or 1/4. Said differently, if you were to look at all of these possibilities, female, female, male, male, female, male, male, female, there are 4 of them, so it would be 1/4 for each if they're equiprobable. Now, this is an absolute abuse of notation because mathematically, when you use set notation, set does not imply an ordering, right? I'm just listing this on purpose. Why? Because you have to decide whether you distinguish female, male, male, female, as being different, or whether you call them duplicates of the same thing. Does that make sense? Okay. And so here, this idea of distinguishing duplicates, you have to answer the question, does the order matter? Does the boy first followed by the girl second, is that the same or is that different from the girl first followed by the boy second? And so this idea of distinguishable order, it means that order matters. They are not equal to one another. And the idea of indistinguishable means that the order does not matter. What you're considering here is the identity, the presence, and not the order. Does that make sense? Okay. So when you're counting, and what I want to do on Monday is have some exercises with this. We do this in class, and maybe we'll try to gamify it. We'll see how that works. These two considerations are really important to how you enumerate the events, be that the total number of outcomes or the favorables for these complex scenarios, where it's not always so straightforward to just look at them like we had with the die roll. Okay. Any questions? Does that make sense? Yeah. All right. And so let's take a look at this idea, and I'm using the word sampling because that mirrors what a lot of statistics books talk about. This is sampling not in the population distribution and sampling case. It's called sampling because you're selecting some object from among a slate of objects. So be that the 3-on-3 football team or the color palette, the crayon box example, you're selecting, and that idea of selection, the word sampling is used for it. Does that make sense? All right. And so with replacement, as we said, says that you replace every selected object back into the initial set. And if you have a random system, all those selections are equiprobable, you can construct probabilities by assuming 1 upon n for each of those selections. Okay. And so you can select, if you sample with replacement, multiple times. So the same individual in the color palette, purple, can be selected twice, for example, in one of those color palettes, A, B, from that example that we had before. Any questions? No questions? Make sense? Yeah? All right. And so the first topic we call permutation. And permutation talks about all of the possible arrangements that you can have that are distinguishable. And that means order matters, right? And so in that case, for permutation, the name implies that if you select female then male, that's different from if you select male followed by female. And so permutation are all the arrangements or distinguishable selection of k objects from a set of n. Now, let's make the assumption that k is less than n. And so in the case of a football team, we selected 3 out of a possible number of 7. So one example of a permutation is, imagine you're selecting 5 playing cards from a full deck of cards, and you want to know how many different hands that you can have, okay? Because those probabilities for things like cards, and a lot of statistics was developed because of gambling and analysis of games of chance, because when you look at hands of cards, a smaller probability is typically associated with a higher value hand of cards, all right? And so there are 2 types of ways of doing this arrangement. There's permutation with replacement, where you put that item back into the set, so it's considered again for the next draw. And there's permutation without replacement, where once you draw it, that set is decreased by 1 because that selection is no longer under consideration for the next draw. It's not available. Okay. Any questions? Make sense? Yeah? All right. So for permutation with replacement, imagine then we're drawing k many times from a selection of size 8. So we have little n possible alternatives. In the case of the crayon example, we had 8 crayons in the box. You could do the same thing with a 64 crayon box. So on each draw, we said with replacement, that size of the slate of possibilities from which you make your selection doesn't change. And so we have n possibilities for the first draw, n possibilities for the second draw, n possibilities for the third draw, up to and including n many possibilities for each of those k many draws. And so we multiply n by itself k many times, and our number of possibilities for this permutation with replacement is n exponentiated to the k. Any questions? Does that make sense? Okay. And that's what we saw with the crayon example. So permutation without replacement is a little bit different. And for that permutation, I almost forgot, for with replacement, you'll notice here this little subscript R on our permutation notation. That means with replacement. That's one of the schemas you'll use in the book I use for this material. It's called Probability and Statistics for Computer Scientists. But nonetheless, permutation without replacement, again, that without replacement says that each time I make a draw, the slate of alternatives or possibilities decreases by 1 on the next draw. And so k many times, we're going to make a draw. And on the first draw, we have n many alternatives. Okay, let me select blue here. So that's my first draw. On my second draw, we have 1 fewer alternatives because without replacement means that once that first draw makes that selection of the first object, it's no longer replaced and can't be considered on the next draw. So that means on the second draw, I have n minus 1 many alternatives from which I can choose. So there's our n minus 1. And on the next draw, it's n minus 2, n minus 3, n minus 4, etc. until that kth and last draw, I have n minus k plus 1 many draws, many alternatives from which I can draw. Right. Does that make sense? Any questions? Okay. And so we can represent this sequence much more compactly, and that's very much desired because, yes, question. N minus k plus 1? Yeah, because when you make your first draw, each time you're decreasing by 1. So you start out with the full n, but if you say n minus k, it's just like when you're adding age, right? If you say someone was born in 2012, if you said 2022 minus 2012 is brain hiccup. Yeah, 2023. If you said 2023 minus 2012, you would get 11, right? But when you start at n many, you have to add 1 more because you don't count that last n point. I don't know if I made sense. Does that make sense? You sure? All right. All right. So, and you could even try this yourself, right? If you started out with 8 items and you wanted to draw 3, all right, 8 minus 3 is 5, right? But if you have 8, you draw the first one, you're left with 7. You draw the second one, you're left with 6. You draw the third one, and I just destroyed my own example, right? Okay. You're counting here, not what you're left with. You're counting the terms that you have because what you're considering is the number of possibilities on each draw, not what you're left with after you draw. Because what we're concerned with is the number of different choices we have on each draw. We're not as concerned with how many you have left after you draw. That makes better sense. Any other questions? Thank you for your question. Any other questions? No? And you'll notice here, you have k many terms. And after you draw k many items, what you're left with, yeah, is n minus k. But the question is, how many choices do you have on each draw? Okay. Now, mathematically, you can represent this more compactly as n factorial over quantity n minus k factorial, where factorial, if you have some integer factorial, that's just the expansion of that integer times integer minus 1 times integer minus 2, etc., until you get to 1. And so if we were to take this expression, n factorial upon n minus k factorial, that going by factorial is n times n minus 1 times n minus 2, dot, eventually we get to n minus k plus 1. And the next term, because it's one less, n minus k plus 1 minus 1 is n minus k. And then we get n minus k minus 1. And we keep subtracting 1 until we get to times 2 times 1. So that's our numerator. In our denominator, we have, and I'll just write it below, n minus k factorial, n minus k times n minus k minus 1. We keep subtracting 1 for each term multiplied times 2 times 1. Okay, and so this term in the denominator, that's n minus k quantity factorial. We have a copy of that for the terms multiplying from above, and that's set of terms multiplied together. That's the same as n minus k quantity factorial. So you have one copy in the numerator, one copy in the denominator. They cancel, goes to 1, and you're left with n times n minus 1 times n minus 2, up to and including n minus k plus 1. Does that make sense? Okay. And so this expression, n factorial upon n minus k quantity factorial, is just an abbreviation for that sequence of the product of terms that we have for the permutation of k objects selected from n possibilities. Does that make sense? And so down below, that's just a mathematical expression. Up above is really what it is. And that mathematical expression is purpose with this being a compact summary, because if you have k terms and k is very large, it takes up a lot of space and it's harder to see. Okay, any questions? Does that make sense? Okay, so this is permutation without replacement. Previous slide, that's permutation with replacement. You can see here that for each draw, the number of terms does not change, whereas without replacement for each draw, the number of possibilities changes. It decreases by 1 each time. Okay, any questions? Does that make sense? All right. So what about the indistinguishable case? We talked about permutation, and for permutation, you're including in your counts all of the orderings. The orders matter. And so in that case, if you selected the first object, then the second, that's different from selecting the second object, then the first. Now, in some cases, when you make a selection, you're interested not in the order, but just the presence of that object. And that's called the indistinguishable case. And that refers to, as we talked about with the family example, of having a boy, then a girl, and then a girl versus a girl first and a boy second, right? In the indistinguishable case, both of those refer to the same selection. And so that's what we use, so-called combination, or N choose K, and C stands for combination. It's also noted differently mathematically as this sort of parenthesized expression, and N is the total number of objects for your slate from which you're selecting, and K is how many objects in your selection. And so if we were to expand this, we have N factorial upon N minus K quantity factorial. Now, if we look at this expression mathematically, we have this extra term here. We have n factorial, we have n minus k factorial, and we have k factorial. And so what this says is take the permutation and account for these duplicates, these redundancies, the different orderings of certain objects that can appear in your selection of k many objects from our slate of n. And so one example, suppose you have a population, I think this was the population of Clark in 2020, undergrad population. You had 1427 women and 922 men. You might ask how many soccer or football teams can you form from this population where the team consists of 6 women and 5 men? Okay, well, permutation says if you're going to select the women, that would be P of 1427, comma 6. But this particular permutation, that counts these different arrangements of particular selections of women from this population. For the men, it's permutation of 922. You're selecting 5. But this also treats different selections of men the ordering is going to matter. But in this case, when you're forming a team, you don't care if John and Gary were selected, or Gary was selected first and John was selected second. For all intents and purposes, in terms of the team formation, it doesn't matter, right? We distinguish them as a duplicate. So you don't want to double count things where the presence of the same set of objects are there. Does that make sense? Any questions? No? All right. And so here we have our permutation, and it does not matter which particular woman was selected. So suppose you have 6 women that were selected. You ask the question, what are all of the arrangements you can have of those 6 women, the particular choice that you have for those 6 slots on the team? And for that, that's 6 factorial, because you have 6 choices for the first of the 6. You'd write that in, times 5 choices for the next, times 4, times 3, times 2, times 1, okay, for that particular set of 6. And so that means now you have to account for that 6 factorially many of those particular 6 women for those slots on the team. You have to do the same thing for the men. You have 5 men that were selected, and for a group of a particular set of 5 men, you have to look at the possible orderings that you can have for those 5. So that's 5 factorial. That comes from 5 choices for the first of the 5, 4, 3, 2, 1. And so you have to account for them, and you account for them by taking that 5 factorial, all of these arrangements. And so when you make these counts, you have to factor this out. And so here, okay, we said our permutation for selecting k objects out of a total slate of n, we said is n factorial upon quantity n minus k factorial. So we call those our distinguishable arrangements, our arrangements where the order matters. So now what we have to do is now discount for all of the possible arrangements, k many, in which those selections, those k many objects can occur. In the case of the 6 women, k factorial would be 6 factorial. In the case of the 5 men, k factorial would be 5 factorial. Okay, any questions? Does that make sense? Yeah. All right. So now we do this for this example for both the 6 women selected as well as the 5 men selected. So here we have 1427 factorial over 1427 quantity minus 6 factorial. That makes it distinguishable where the order matters. And then we discount that by dividing by 6 factorial. So now the numeracy, the counts of all the possibility, assumes that we don't care if the same group of women, what order they were picked. We're not distinguishing them. We're calling them duplicates. Does that make sense? Any questions? No? And likewise with the men, 922 factorial over quantity 922 minus 5 factorial. That is the distinguishable portion. And then we discount that by 5 factorial because we don't care what particular order the 5 factorially many men were selected for a particular selection of men. Okay. Does that make sense? Yeah. So then we would multiply what our indistinguishable count is for the women part of the team by the indistinguishable part for the male part of our team. And so here, in more compact notation, we have 1427 choose 6 times 922 choose 5. Okay. Any questions? Yes. Yes. When you do the selection instead of, so if in the case, if the women part of the team was distinguishable and the men's part of the team was indistinguishable, you just use the distinguishable selection, the permutation for the women's part, and then you use the combination, the indistinguishable version for the men's part, and it's still multiplicative. Any other questions? That makes sense? Okay. And so properties of combination, and I'm going much faster through this than I originally anticipated. This is our formula compactly for combination. And if you were to choose 0 items with indistinguishably from a slate of n objects, there's only one way to choose nothing, right? Okay. You could just memorize the fact, use reasoning, or if you plugged in k is equal to 0, you get the same result. Likewise, if you were going to choose one object indistinguishably from a slate of n possibilities, there are n ways to do this because you could choose the first one, the second one, the third one, up through and including the nth one. If you plug this in, the mathematics works out. The indistinguishable arrangement is going to be little n. And then this last property, you'd have to plug in, prove it to yourself. It does hold true. Choosing k objects from a slate of n indistinguishably is the same as choosing n minus k objects indistinguishably from a slate of n. And if you plug in here, and if you want to prove that to yourself mathematically, when you plug in for this version, you should put n here, but the k term, instead of saying k, you'd say n minus k here. And so each time when you plug in, you're using these values, so that'd be n factorial. Everywhere you see k, n minus n minus k factorial, and here you're going to say n minus k factorial. And so this is your n term, and this would be your k term, and you just do that substitution, and the math works out. Okay, any questions? Does that make sense? So I encourage you, particularly for this last identity or property, to prove this to yourself. Okay, any questions? And so this permutation, this version of combination is combination in indistinguishable selection without replacement, meaning that when you make a selection on the next draw, it's no longer available for future selection. And so this last one, people usually don't cover, I think it's important to kind of round this out, is so-called combination with replacement. And with replacement goes back to that color palette example, that we gave, where each draw sees the same number of items from that slate from which you're making your selection, right? And so how many collections can you form choosing k many objects out of a slate of n with replacement? That means you can have the same object appear more than one time because that set does not change from one draw to the next. Does that make sense? And so for that, I'm going to use an abstraction, and it's very popular, at least in stochastic considerations, so-called balls and bins treatment. So suppose you have a slate of n many objects. You have the first object, the second object, the third, and so forth, up to and including the nth object. And what we're going to do is we're going to make it easy to identify a selection for a particular object by drawing these vertical bars. You can almost think of them as these dividers, right? They're going to define these slots. It's almost like a carnival game, right? You have these slots, and the first slot represents the first object. This is our first slot here on the left, your left. The second slot or space between these vertical bars or these partitions refers to your second object. And then this last slot here on the right of this last partition refers to a selection of the nth object. And so now the question is, how many dividers do we need to represent these n many slots, right? We need n minus 1 dividers. Because if you think about it, if we have a slot on the left-hand side of each divider, well, we have a slot here, we have a slot here, have a slot here, and so forth. This last one is n minus 1, because there are n minus 1 dividers if we represent n minus 1. And then this to the right of this last one, that's going to be our nth slot. And so in order to have one space representing each one of the objects, we need n minus 1 of these partitions in order to represent slots for these n many objects. Does that make sense? Any questions? No? So now That's the number of alternatives, n minus one slots, n minus one dividers. So now to represent those case selections with replacement, imagine that you're blindfolded. And because you're blindfolded, you don't have a preference for any particular slot. You're not sort of aiming for one or preferring one of the slots. You're going to toss this ball, and each ball represents a selection with replacement for one of the objects represented by one of these n many slots. And so if a ball lands in a slot, that represents a selection of that particular object. And so here in this depiction, we means that we've selected the second object. And so because you're not preferring any particular slot over another, you have k many balls representing your selection. This next selection means or represents a selection of the first object. So the first draw was the second object. The second draw was the first object. Because none of the slots are preferred, you keep throwing balls until you throw a total of k many balls for your selections. And you can select the same object multiple times because it's with replacement, just like the crayon example. And so in this particular case, you've made another selection. Your third selection was a selection of the first object again. Because it's with replacement, on each consideration, in this case, each throw of a ball, you can select the same object more than once because all of the alternatives are available for each one of the selections. Okay, any questions? Does that make sense? The configuration? Okay, so now if you toss a ball and a ball does not land in that slot's going to be empty, right? If a ball is in that slot, that ball in that slot represents the selection of that particular object out of the n many alternatives. So we have n minus one dividers, and after we throw all the k many balls, we have a configuration that looks something like this. In this case, this object, that first object, was selected 2 times. This object was selected 1 time. This object was not selected 0 times. And so when we toss the k many balls, some slots are going to have a ball, some slots are going to have more than one ball, and some slots are not going to have any balls. And that represents the number of times that particular object was selected. And so this idea of so-called combination with replacement is an indistinguishable arrangement of k many objects selected from among n many alternatives. But in this case, we don't distinguish the duplicates. We count the presence of the selection, but not the ordering of the selection. Does that make sense? And so I'm going to show you the answer and then explain how we get to this answer. And so you use combination, the same combination we talked about before for the without replacement. We use that in order to compute combination with replacement. And so here we take our n minus 1. Oops. We take our n minus 1. Oops. Where'd it go? I lost my pen color. There we go. We take our n minus 1 for the number of dividers. We take our k for the number of balls. We add them together. And so, then we take our k, the number of balls, and we use that as the number of choices. And this expression, I'll explain where it comes from, but that's how you compute combination with replacement. You change what this first parameter was to our expression for combination. First, does that notation make sense? Any questions? No? All right. So let's take a look at where this comes from. And so if we want to consider this problem, what we're asking is using this configuration, you can think of it as a string of balls, there's a ball, and dividers. And so if we were to look at all the possible ways to do this selection of k objects, k selections out of n objects with replacement, what we're interested in is all the possible ways we can arrange these balls and these dividers. And so in one arrangement, we might have the following. we might have k many balls for the first object, and all the other objects, nothing is selected. We could have one k minus 1, k minus 1 for the first object, 1 for the second object, and then nothing for all the others. And so if we consider the fact that we have n minus 1 dividers, or these vertical lines, and we have k many balls, to ask how many ways we can do this combination with replacement, another way of asking that is how many arrangements can we have of these balls in these vertical bars? Does that make sense? Any questions? All right. And so here we want to arrange these balls in these dividers. Now for these balls and dividers, when we arrange them, we have a total of k plus n minus 1 things that we can arrange. But we notice that we have balls and we have dividers. It doesn't matter what the order of the balls are. So in that case, if I had k balls for the first object and no balls for all the other objects, it doesn't matter if I have ball 1, ball 2, ball 3, etc., or if I have ball 2, ball 1, ball 7, etc. It doesn't matter what that arrangement is. So if I look at all possible arrangements of balls and dividers, I need to account for these duplicates because the order doesn't matter which ball comes first, which ball comes second. What just matters is that it's in a particular slot. Does that make sense? Likewise, for these dividers, if I have my dividers, it doesn't matter what the ordering of the dividers are. What matters is that I have a certain ball in my divider, right? And so in that case, I need to account for the particular arrangements, the way I can arrange my bars. Okay. And so here I have my distinguishable arrangements of all of the things, balls and dividers that I can have. And it's k plus n minus 1 factorial. That's a distinguishable arrangement. That's a permutation. And then I divide by the number of arrangements of the bars. And I also divide by the number of arrangements of the balls, because the order of the balls and the order of the bars does not matter. And wait a minute, I get exactly this expression that I started with. And so this construction, it uses our combination without replacement, that function, but we treat it a little differently in terms of the parameters that we give to it to represent this configuration is how we model these scenarios. Any questions about that? Does that make sense? No? All right. Yes? All right. So we have 15 minutes left, and I was really budgeting for more questions, but I have no problem ending the class 15 minutes early. So why don't we do that? If no further questions, I'll see you all on Monday. Have a great weekend. Please take a look at the reading, and I'll try to figure out over the weekend an in-class exercise for some of these counting things, see if I can gamify it. We'll see what happens. So see you all on Monday. Have a great weekend.